Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 6 of Aero 3271. Today we're going to be continuing our study into fatigue, and we're going to look specifically at cumulative fatigue damage and how we put together all the things we've learned so far. We're going to learn how to take our initial characterization of the fatigue curve, the SN curve. We already know how to calculate a more accurate endurance limit and to change it into something that simulates our sample in real life. We know how to take now fluctuating stresses or stresses that aren't just fully reversed and convert them to fully reversed stresses equivalent fully reversed stresses as we evaluate infinite life versus the number of cycles we might have. And now we're going to look at if we have completely different kinds of stresses, how we will characterize each in the way we've learned to do, but then put them all together for evaluating the fatigue life and or damage. So far, what we've learned is we've learned how to characterize our completely reversed stresses, our repeated stresses, and we've also learned to look at the general fluctuating stresses. These three types, where the general kind of covers everything, we characterized these basically by finding the maximum and the minimum stress. We get the max-min stress, and we calculate the mean and alternating components of stress. We then apply any stress concentration factor that applies, and we use those two characteristic stresses, the mean and the alternating, in order to evaluate fatigue. Of course, what we've learned so far means we can only evaluate one kind of stress. Sure, we can evaluate any type, but we can only evaluate that one type. And we couldn't look at how it might combine with a completely different set of stresses. But today we're going to fix that. So let's take a look at a little cycle like this. Let's say we have, and this is actually a very small and short set of stresses that would probably not cause fatigue, but let's just say we have this cycling of stress shown in the figure, right? If we look at that, we might ask ourselves how we can evaluate this. Is this one cycle, two cycles? What's the max and the min? And will that account for everything that's happening? So if you asked ourselves this question, how do we evaluate it? Do you think we would evaluate the cycle with the highest mean stress? Or should we evaluate the one with the lower mean stress? That seems stupid. Or should we evaluate the cycle with the largest alternating component? Or take the max and min of everything and analyze that, right? Well, what we're going to do is go beyond this and learn how to put these things together. So let's look back at our little cycle. Basically, Miner came along, and then a guy named Palmgren came and changed it slightly. And what these guys said is that we can treat this as the damage each cycle causes and put them all together. If you've ever played Dungeons and Dragons, you know exactly what I'm talking about, because every character has a number of hit points, and every time they're struck, they lose some hit points. And as long as their hit points don't go to zero, they're still alive. And over time, they repair, and then you can go to a cleric and get healed and all that nonsense. Actually, World of Warcraft does the same thing, but it does it all behind the scenes. You can see your little health dropping or webbing and ebbing and waning as you go through the course of the game. Well, structures are people too, and if you have a cycle, it causes damage or potentially causes damage, and if it does cause damage, that cycle, that damage will accrue. Now, damage in structures doesn't fix itself. It actually just gets worse. Just gets worse unless we do something to repair it by adding energy. But that's beyond what we're going to do here. All we're going to do is say, hey, if there's damage, it accrues and it adds. So we're going to learn how to add those things together. Basically what we're going to do is we're going to come up with a factor. The way we're going to evaluate the damage of each cycle is we're going to come up with, well, if you have, let's say we have one cycle going to failure. If we have the allowable number of cycles, we could call that capital N. And the actual number of cycles we have, that we call that little n. If little n is the same as capital N, then the factor is 1, and that means you have loaded the thing up right to its allowable. It survives, but barely. If that factor is greater than 1, you now have one more cycle, one or more cycles beyond the allowable, and you can expect failure. If this factor is less than 1, then you did not fail based on that cycle. And if this is true, what we can do is just take the number of cycles over the allowable cycles for one stress, and then look at another stress, and then say, well, we have the number of cycles that happens there versus its allowable, and so on, and adding them all together. And if we add those together, we can expect, if the number is 1 or less, we're good. Good to fly. Not going to fail yet. Or, if that factor is greater than 1, we can expect failure. Now, testing has shown that actually the way this comes together is not exactly a 1.0. Some structures or some stresses can actually cause failure something less than 1. And if we call that cumulative damage D, capital D, damage a little less than 1 down to about 0.7, and maybe as high for some structures as being able to get up to a 2.2 factor. Of course, in order to spread it beyond what seems analytically correct or intuitively correct, we would need test data to support that. So what we're going to do is just imagine D is 1. So if our damage accrues to 1, we're good. If our damage accrues to more than 1, we're going to expect fatigue failure. And if our damage accrues to less than 1, we're going to expect the structure to survive. That's going to be our approach. Got that? Don't worry, we're going to see how this plays out as we go forward. Now, if you also look at testing, as you might also intuitively think, whichever cycle has the largest range, largest cycle, obviously the max and the spread are going to be two things that matter. If we could characterize like the largest maximum to the largest minimum, that's going to seem to dominate. So what we're going to do is not just look at the little cycles and how they go and treat each one like this, but what we're going to do is find like a maximum and a minimum, define that as one cycle, and then kind of separate the other pieces in a similar fashion. Let's see how that works. So let's go back to our little stress scenario. How many cycles do you think we have? 1, 2, or 3? Well, it looks like I already spilled the beans by pressing too many buttons. Let's take a look at why that's true. We want to know how many cycles we have. What we're going to do is we're going to draw our little diagram and we're going to connect the dots, okay? So you'll notice these look like two separate sets of stresses, and we're going to just connect them as shown with this nearly vertical line here. Then what we're going to do is going to move some fragments until it looks like a nice continuous movement from one point to another with no backtracks. So if we do that, we just slide this first little segment over to the right, and we find this one. Then what we're going to do is pick up the scraps, and we're going to define the largest cycle. You'll notice here that what we did is we started right at the top. In this first one, you'll notice we just took this little fragment here and we moved it over to there, right? And that gave us something that started from here, went in a continuous path downward, and then came back up. Okay, now when we get to this third one, picking up the scraps, what we're going to do is first define the largest sample, the largest cycle. We're going to start here, and we're going straight, not going to backtrack. We're not going to backtrack, so we just stay at that level and keep on going. And then they keep going, and then come up, not going to backtrack, so we go on over. We're going to call that cycle number 1. Then we're going to come back and see, what did we miss? We see, oh, we missed this little fragment here, so we're going to take that little one, and that will be cycle number 2. And then we'll see, oh, we got one more fragment. We'll take this little guy, and that'll be fragment 3. You got that? Now with that said, that means we now can define our cycles. Our first cycle goes from a maximum of 80 down to a minimum of minus 60, identifying the maximum in. Our second cycle goes from a maximum of 60 to a minimum of 40, and our third goes from a maximum of minus 20 to a minimum of minus 40. We look at our diagram, it looks like we picked up all the scraps, so this is everything we need to analyze. We have 3 cycles. Let's take a look at how we put these together on the next slide. So here we are, we've identified our cycles. And now what we're going to do is characterize these. Now that we've identified these, now this is already assuming that those stresses that we're seeing include any factors of safety, and that we've also applied any stress concentration factors to those, okay? That's these stresses are the maximum stresses that have been factored, okay? Now that we've done that, we can take these and characterize our stresses for each. We take the maximum in and calculate the mean. And we calculate the alternating. You guys should be able to do that from our prior lecture. Now that we have the mean and the alternating, what we're going to do is select a failure mode. We're going to select a failure mode and calculate the margin of safety against infinite life. What we see is our first cycle has a negative margin of safety. If any of these have a negative margin of safety, that means it won't last forever. That means while cycles 2 and 3, if they were acting alone, would not cause anything close to failure, cycle 1 causes failure in itself, therefore the whole thing will not survive in fatigue. Not for ultimate life, not forever and ever. It will stop cycling before it gets to heaven. Got that? Okay. Now, what we're going to do, all that means is we have more work to do, because while this doesn't have a positive margin for infinite life, it may be sufficient for the life that's required of the aircraft. So now what we're going to do is calculate what's the allowable for each cycle. So we can take the FM and the FA for each cycle and plug it into the equation for the fully reversed stress using the same failure criteria, and we calculate the equivalent fully reversed stress as shown in this column. Then we can take that fully reversed stress, we can go and look at that stress against our FFTU to determine from the SN curve whether each cycle is high or low cycle fatigue. If it's low cycle fatigue, we need to use those two coefficients A and B in our equation. And if it's high cycle fatigue, we need to use those coefficients A and B. And then we use those values to calculate the allowable for each cycle acting alone, which is shown here. Now, because these two, now you got to be careful here, you'll notice these next two, the last two stresses, now if you just plug in, obviously those are not low cycle fatigue, and they're really not high cycle fatigue. What students tend to do is grab the high cycle fatigue coefficients and apply it to those stresses, and they will end up calculating a life. But remember, if that life is over 10 to the 6th or a million cycles, what that means is that it actually should experience infinite life, especially if it's a steel. So instead of placing some arbitrary number here, since these two numbers are both below the endurance limit of the material, that means those will survive forever. That means they cause no damage. Okay, you have to be careful of that, or you'll tend to get mess up your otherwise good work. Now that we know the number of cycles for each, we can calculate the damage that each cycle causes. We do that by just taking the ratio of the number of cycles to the n. Now in this case, each of these cycles was only 1, but it could have been 10, it could have been 100 cycles, it could have been 1,000 of each, right? Whatever it is. In our case, we only had 1 of each cycle, but in other cases there may be many more. Okay? All right. So with that said, we calculate the n over capital N ratio. We plug it into our table. We then sum up the damage. What's the cumulative damage? We just sum this rightmost column. That tells us how much damage is done. And then we can write the margin of safety as 1 over the damage minus 1. Got that? So the total number of cycles that this part will be good for. Now, if this part was only exposed to the first cycle, it'd be good for 614,192 cycles. If this is experienced all of them, it will be able to withstand 614,191 cycles of the entire thing. Now, you might ask yourself, well, why did the number of cycles not change? Well, the reason it didn't change is because cycles 2 and 3 in this particular example didn't cause any damage. In other cases, it will have a different life based on all the cycles that occur. Does that make sense? So we see here how to calculate the total cumulative damage. We see how to calculate the actual number of cycles for the entire system, and we see how to calculate the margin of safety. Things we ought to be able to pull out of this table. If I ask you how many cycles can this part withstand of cycle number 2 acting alone, you'd say infinite. If I ask the same question for cycle 3, you'd say infinite. If I ask you how many cycles can this withstand of cycle 1 alone, you'd say 614,192. If I ask you how many cycles of this entire stress spectrum can this withstand, you'd say 614,191. And if I ask you what the margin of safety is, you just take that minus 1 over that minus 1. Okay. Here is, so what this slide does, and this tends to confuse students, actually this really brings to light what we're trying to do here. It makes it clear. This, I'm going to call this Miner's incremental rule, but actually this is not Miner's rule at all. It's just showing how Miner's rule works. And the way it works is like this. If we come in here, remember we have the SN curve, and we'll notice we're focused on from 10 to the 3 to 10 to the 6 cycles. This is high cycle fatigue. Now remember the slope of the curve, it's going from our point FTU down to our endurance limit. The slope of this is B, and the intercept is A, but the intercept is on the one cycle, not 10 to the 3rd cycle, okay? So we look at this curve, this upper bold curve is our allowable. If we come in here with a stress level, let's say we have a stress sigma 1 for a certain number of cycles, we can plot sigma 1 for the number of cycles as shown here, right here. So if we are given that something, our part has a stress sigma 1 and it's applied for n1 cycles, or let's use a lowercase n, we would come out here to n1 cycles on the long curve and plot our point. Now we can see that's inside the SN curve, therefore it's good. What we're now going to do is calculate, well, for that stress level, that fully reversed stress level sigma 1, let's calculate the allowable. Remember, this is a lowercase n. Let's calculate the allowable for that. That's this point over here, right? Now we can say, well, this much damage was done, this much damage is left. So we can take this allowable, n, minus this number of cycles we had, n, and that gives us the remaining life for that cycle, okay? So we can, using our stress level, we're going to use A and B once we've determined whether this is high cycle fatigue. Now in this particular case, this is high cycle fatigue. We can tell because we're between 10 to the 3rd and 10 to the 6th. We can calculate our n, our allowable for that, and we calculate the cycles that are left. Remember, this here is n1, this point here, and this is here is n minus n1. Okay, that difference. Okay, now what we can do is draw a line. Now that we have found the n left, we can draw a line through this point here. It's got, now what Miner's rule says is it has the same slope B, but because it moved, it's going to have a different intercept out there. So now what we're going to do is calculate a new intercept for that n left by plugging in our B and our n left and our sigma 1. Then we can calculate a new endurance limit. It's going to change the endurance limit. It's down here when we slide this curve, changing the endurance limit. And then if we have another stress level, we can do the same thing. We'll go and we'll say, okay, if we have another stress, we plot that against it, and now we're doing the same thing. So we're going to calculate N2 for the new one using the A prime that we got. And I'm going to erase this stuff on the slide since that's messing with my cursor. Then we're going to have calculate N left for that, and then we could calculate a new A, a new intercept, using that stress level and the n left from that one, and then we can calculate new endurance limit, and so on and so on. This is how the method works. If I tell you to use Miner's incremental rule to calculate the fatigue life, you will use this method. If I tell you to use Miner's rule, you're going to use the method that I showed you before. We just put a table together and tabulate that, okay? Is that clear? Now, regardless of which method you use, you're going to get the exact same answer if you do it correctly. However, this method is much harder to apply for most people, and if you make a mistake, it's harder to unravel how much effect that had. So you will lose probably more points if you use this method and don't get it right than you will if you use Miner's regular method. Okay, you hear that? All right. I'm going to show you one other method. It's called the Manson Method, and it does a similar thing. The Manson Method follows a similar approach. It looks at some of what people think are shortcomings of Miner's rule and corrects them. So basically what it does, we're going to have a similar step-by-step procedure. We're going to start by looking at the same SN curve, which is shown here. Remember, here's our SN curve in the high cycle fatigue range. And we're going to plot our stress as before, right, which has an N and a sigma value. And we're going to use that same N, calculate a new N minus N1. Those parts of this method are all going to be identical, and that's where it's going to switch. Because where before, what we did was come along and with Miner's method, I'm going to draw it over here, our SN curve here. With Miner's method, and this is Manson's method, with Miner's method, after each stress level, we place this new curve parallel to the first one through that point, stress level N minus N1. In this case, what we're going to do is now pivot about our FFTU. So in this case, we use the same exact B, but we change our A. In this case, for Manson, we're going to change both A and B as we go through this approach. That's going to end up giving us a different result, and some folks will say it does a better job of aligning with test data. Okay, so here's our approach. We're going to plot our stress. Now, we're actually not going to plot it. What we're talking about plotting it is making it visually, so we can visualize it. What we're going to do is tabulate it, but we're going to calculate it. So we're going to calculate our stress 1 and the N1, and then we're going to calculate the A and B for that. We're going to calculate the allowable number of cycles for that, and we're going to calculate our N left by subtracting the allowable number of cycles minus the applied number of cycles. All that's the same as Miner's. Then we're going to deviate, because now what we're going to do is, now the way the method works is it draws a line through that point pivoting on the FFTU point. But what we're going to do is not draw the line at all. We're just going to calculate this new B prime, the second B, or we could call it B2, right? So we're going to calculate a new B, and it's going to be, now this is assuming that our FFTU point is at 0.9 times the FTU, right? If it actually we had a different F, it would be pivoting about a different point. We're just going to go ahead and use this 0.9 FTU for if we use the Manson method regardless of material. So B prime is just going to be calculated here. Once we have B prime, we'll use B prime and N left to calculate our new A. We now are going to use both the A and the B to calculate what the new endurance limit is. And then if we have another cycle, we will do the same process, calculating its allowable using the new values of A prime and B prime, its N left using the calculated value, calculate a new B prime, a new A prime, and then continue. That's the Manson rule. So we have 3 methods for evaluating fatigue. We're mostly going to use Miner's rule, and to do that, we're going to tabulate our stresses, our max stresses, our allowable, our margin of safety, and then the number of cycles to failure, and then the damage of each, sum the damage of each, and then evaluate either the number of cycles allowed or the margin of safety. The only time we will use these other 2 methods is if I ask you to use those methods. And what I will say is use Miner's incremental rule, which means use the approach given on the slide, the last slide. or I'll say use Manson's rule, which means use the approach shown right here. Now, these last two methods, Miner's incremental and Manson's, only work the way I've defined them here, only works in the high cycle fatigue range. It will not work for low cycle fatigue. So if you try to apply these methods to low cycle fatigue, it will not work. That doesn't mean they can't be used to do that, but we would have to come up with a more elaborate procedure to deal with that case. Got that? So, with Miner's rule, we can estimate, we know that cumulative damage is given by this equation, and it has to be less than 1, and our margin of safety is written this way. We've talked about all this, okay? We can also write our margin of safety like shown below. It's the number of cycles allowed over the number of cycles needed minus 1. Those are how we evaluate fatigue. Let's say we have a simple example, and we want to evaluate it. Here's how it works. We first get our FTU and our S sub E prime we calculate. We get our F, or our stress fraction, and we calculate our pristine endurance limit. We turn that pristine endurance limit into an actual endurance limit by applying Marin factors. Once we have that, we tabulate how many cycles of each and what the stress levels are. Now, if we don't know the sum number of cycles, if like in the case given, we go back and look at the problem statement, what we were asking for is, after a certain stress level with 80,000 cycles, how many of this other stress level are we good for? That's a slightly different characterization of the problem. The way we solve this kind of problem is going through the same procedure with a slight tweak. What we're going to do now is we're going to say, okay, well, we don't know how many cycles of the second one we have, but we can still apply our procedure. So we're going to start by calculating our mean and alternating stresses of each, and then we're going to choose a failure criteria, and we will evaluate the margin of safety. Once we do that, we will, if we have a negative margin of safety for either of these, we will calculate the equivalent stress, fully reversed stress level, using the same margin of safety, or the same failure criteria to calculate that equivalent stress level. We then will use that stress level, determine whether that's high or low cycle fatigue by comparing to the FFTU value, and then calculate using the appropriate coefficients. We will calculate the number of cycles to failure for those cycles acting alone. We then tabulate how much damage is caused by each. Now we can see how much damage is caused by the first, but since we don't know how many cycles we had for the second, we don't know how much damage. So here's where we're going to tweak our approach for this kind of problem. Okay? What we're going to remember is that the sum of the damage is written this way, and that means the damage left after the first cycle is just 1 minus the sum of the damage of all the other cycles. Therefore, that means since the damage left is just N2 in this case over the allowable N2, then we have this equation which we can rearrange this way and then solve for N2. N2 becomes the allowable number of cycles that we can have for stress level 2 if the part already experienced the first cycle stress. Okay? Now, if we think about this a minute, so that means it can take 6,000. That means we would put 6,000 cycles in this table. Okay, so let's ask ourselves some questions. How many cycles can this part withstand of stress level 1? If you look at the table, you can see it's 145,811. If you ask, how many cycles of stress level 2 can it take? It's clearly 15,491. If you say, how many cycles of stress level 2 can this withstand after stress level 1's 80,000 cycles, then the answer is 6,992. You see the difference? If cycle 2 acts alone, it's good for 15,000 cycles, roughly. But if cycle 2 follows this other stress level, cycle 1, and 80,000 repetitions of that, then it's only good for 6,992 cycles, because cycle 1 damaged the part. Got that? Okay. All right. Now, if we wanted to solve this same exact problem using Miner's incremental rule, we would also construct a table, and it would look like this. The first part of our table would look the same. We'd get our A and our B, we'd place those in the table, we'd calculate our fully reversed stress, our number of cycles. You notice the number of cycles there is correct, right? That gives us N left. So in our first case, we see we can kind of tabulate everything. We can kind of tabulate everything before we start calculating. But in Miner's incremental method, what we're going to do is calculate each row by itself before the next row. So we calculate N, we got N, A, B, stress rev, allowable, number of cycles left. Then we go down, we don't know what this is, but we're going to use the same B, and we calculate our new A. We're going to use that new A and the B to calculate this, and then get this from that. And that gives us the same answer. You'll see this, calculated in this manner, gives us the same answer as Miner's incremental rule. However, Miner's incremental rule has more chances to make mistakes, and more places where you're not understanding it can affect what you're doing. Okay? Now, if we're going to use, we get the same answer. If we're going to use Manson's rule, we're going to follow a similar approach. Once again, we're going to start in the same manner as we did by just calculating this first row, which you can see is the same. But now we're going to use N left and everything we found to calculate a new A and a new B. Use those to calculate the sigma rev, which gives us a totally different number of cycles. You'll see that this process gave us a completely different answer for the number of cycles. Now, this, what Manson proposes, is that you could be good for 10,000 cycles of the last cycle. Okay? So these are our three methods. The first one we're calling Miner's rule. The second we're calling Miner's incremental rule. Although it gives the same number, don't use that unless I ask you to use that, unless you're just experimenting on your own, okay? And then Manson's method, which gives a different number. Those are the three ways that we're going to apply these together. Mostly we're going to use Miner's rule the way in the most straightforward fashion, okay? And if you understand how to, some companies will do fatigue a little differently, but many of them will follow. Everybody will pretty much understand, if they know anything about fatigue, how to use Miner's rule, and you guys will be armed and dangerous with being able to calculate meaningful margins of safety for fatigue. Got it? Enjoy.